Cookbook for the Universe. The Chemistry of the Stars. The chemistry of the stars is the cosmic alchemy that shapes the universe, where the immense pressures and heat of stellar cores fuse simple elements into complex ones. Hydrogen ignites to form helium, releasing energy that fuels the brilliance of stars. As stars evolve, fusion creates progressively heavier elements: carbon, oxygen, neon, and iron, each step governed by the intricate balance of energy, impedance, and resonance. When massive stars reach their limits, they explode as supernovae, scattering gold, platinum, and uranium across the cosmos. These stellar ashes seed new worlds, forging the elements of planets, life, and the very fabric of reality. By Orion Carl Daly. 1. Aka, Essay on Relative Gravity to describe the mechanics of the universe. Stellar nucleosynthesis, relative gravity, and the chemistry of the stars. From the dawn of time, the heavens have captivated human curiosity, their glittering constellations whispering stories of cosmic origins. Yet, beyond their brilliance, stars are more than celestial beacons. They are the universe's alchemists, transforming the simplest atomic matter into the vast atomic mass spectrum of elements that compose planets, life, and the very fabric of reality. This intricate and awe-inspiring process, known as stellar nucleosynthesis, governs the chemistry of the stars, the formation of matter, and the evolution of the cosmos. At the heart of the chemistry of the stars is an interplay of nuclear fusion, energy exchange, and elemental transformation. Hydrogen, the most abundant element in the universe, serves as the primal fuel of stellar engines, igniting in the intense gravitational crucibles of young stars. Through nuclear fusion, hydrogen fuses into helium, unleashing tremendous energy that counteracts the force of gravity, allowing stars to shine for billions of years. But the story does not end with helium. Each stage of stellar evolution forges progressively heavier elements: carbon, oxygen, neon, and silicon, culminating in the formation of iron, the final stable nucleus. However, iron marks a cosmic threshold. Unlike its predecessors, iron cannot be fused to release energy. It signals the star's impending collapse. When massive stars exhaust their fuel, they explode as supernovae, dispersing their enriched cores into the interstellar medium. These cataclysmic events birth the heaviest elements: gold, platinum, uranium, through rapid neutron capture, seeding future generations of stars, planets, and even life itself. By Orion Carl Daly. 2. Cookbook for the Universe. 1.1. Applying the Relative Gravity (RG) Framework. Yet, while classical astrophysics effectively describes these nuclear processes, it remains incomplete in explaining the deeper structural and dynamical relationships governing stellar evolution, energy exchange, and matter distribution on a universal scale. The relative gravity (RG) framework expands our understanding by introducing impedance, resonance, and superposition as key principles that govern not only how elements form, but also how energy and forces interact across different states of matter in the cosmic fabric. 1.2. Bridging stellar chemistry and relative gravity. Relative gravity posits that all forces share a common parent property, relative force, and that stellar evolution is not simply a sequence of thermonuclear events, but rather an interplay of relative equilibriums within spatial time, energy flow, and impedance gradients. This perspective enables a more comprehensive understanding of why fusion follows distinct pathways within different stellar environments, how impedance regulates the rate and efficiency of element formation, why certain elements are more abundant than others, how energy is distributed and recycled across the cosmic network of stars, supernova, neutron stars, and black holes. In this framework, stellar nucleosynthesis is not an isolated event within individual stars, but a dynamic, interconnected process influenced by energy superposition, resonance interactions, and impedance differentials across time and space. Every star, from its birth to its death, acts as a node in a larger network of energy and matter cycling through the universe, shaping the cosmic environment. 1.3. Reinterpreting stellar evolution through impedance and resonance. By incorporating relative gravity's object-oriented approach, we can view nucleosynthesis as an expression of harmonic resonance between relative forces rather than simply as a product of gravitational compression and nuclear reaction thresholds. In this model, the formation of elements is dictated by relative force interactions, not just temperature and pressure, but also how energy pathways align within a star's structure. By Orion Carl Daly 3. Aka, Essay on Relative Gravity to describe the mechanics of the universe. Impedance serves as a governing factor determining which fusion processes are favored or inhibited based on energy constraints and resonance states. Supernova function as cosmic capacitor discharge events, where energy is not randomly expelled but follows structured patterns of impedance breakdown and field realignment. Gravitational waves and neutron star mergers act as high-frequency resonant amplifiers, facilitating the synthesis of the heaviest elements. This holistic perspective redefines stellar nucleosynthesis as a cumulative, resonant process embedded within the broader continuum of relative gravity, where stars are not merely energy sources but structured manifolds contributing to an evolving universal equilibrium. 1.4 Exploring the sections ahead. With this foundation established, we now delve into the core aspects of how stellar nucleosynthesis aligns with relative gravity. 1. Fusion as a function of relative force. Understanding how element formation is driven by relative mass interactions and energy distributions, rather than traditional gravitational compression models alone. 2. The role of impedance in element formation. Examining how resistance to energy flow within stellar interiors determines the efficiency and sequence of fusion reactions. 3. Supernova as alternating current events. Reinterpreting supernova explosions as dynamic phase transitions in cosmic energy exchange. 4. Neutron star mergers, black holes, and the delta phenomenon. Exploring how extreme environments create the heaviest elements and reshape matter-energy relationships. 5. The universe as a stellar nucleosynthesis network, demonstrating how nucleosynthesis extends beyond individual stars, forming a vast interstellar system of energy cycling and element distribution. The chemistry of the stars is the chemistry of existence itself. It is the great cosmic symphony of matter and energy, revealing how the elements that compose our world, our very bodies, were once forged in the hearts of ancient stars. By Orion Carl Daly 4. Cookbook for the Universe 2.0. Fusion as a function of relative force. In the framework of relative gravity (RG), all forces share a common parent property, relative force. This perspective shifts the conventional understanding of nuclear fusion, traditionally described as the strong nuclear force overcoming electrostatic repulsion, toward a broader view where fusion occurs as an expression of relative equilibrium between interacting forces within the stellar manifold. While classical physics explains stellar fusion as a consequence of gravitational pressure compressing atomic nuclei to the point where quantum tunneling allows fusion to occur, relative gravity redefines this process as an interplay between relative mass, impedance, and resonance, where energy pathways dynamically balance across spatial time. 2.1 Conventional versus relative gravity perspectives on fusion. Conventional model standard physics. Fusion occurs when extreme gravitational pressure and thermal energy force hydrogen nuclei protons close enough to overcome their mutual electrostatic repulsion. The strong nuclear force then binds them together, releasing energy as part of a stepwise nucleosynthesis process. The efficiency of fusion is dictated by temperature and pressure in the stellar core, the density of nuclear material, the probabilistic quantum tunneling of particles through their electrostatic barriers. 2.2 Relative gravity perspective. Instead of treating fusion as solely a function of temperature and pressure, relative gravity considers it a function of energy equilibrium governed by cumulative relative forces acting within the stellar manifold. The impedance profile of the stellar plasma, which determines the efficiency of energy transmission and transformation. Harmonic resonance states, where wave-like interactions between mass-energy fields optimize fusion conditions. Heat insight, rather than an indiscriminate reaction occurring under extreme conditions. Fusion follows structured energy pathways dictated by relative equilibrium points, where impedance is minimized and efficiency is maximized. Relative equilibrium in stellar fusion. Instead of Newtonian gravity being the primary driver of fusion pressure, relative gravity suggests that fusion occurs at points of relative equilibrium, where interacting forces reach a harmonic energy balance, allowing energy conversion to occur with maximum efficiency. This aligns with the idea that stellar interiors function as resonant cavities, where energy does not simply accumulate as random thermal motion, but oscillates in structured patterns before transforming into higher-order elements. M1D2 equals M2D1, where M1 and M2 represent relative masses of interacting plasma regions. D2 and D1 represent spatial distance relationships within the stellar manifold. This equation describes the equilibrium point where energy flow stabilizes, enabling optimal fusion conditions. 2.3.1 Implications of relative equilibrium in fusion. At these equilibrium points, fusion efficiency is maximized, influencing A. The structure of stellar layers. Different layers within a star correspond to harmonic zones where fusion reactions shift based on relative mass density and impedance balance. This explains why stars transition from hydrogen fusion in outer layers to helium, carbon, and beyond in deeper layers. Each element formation is tied to the impedance constraints of its environment. B. The rates of element production. Classical models describe fusion rates as dependent on temperature and pressure alone. Relative gravity suggests that fusion occurs more efficiently at resonance points, where impedance aligns with energy wave patterns, preventing excessive losses through radiation and neutrino emission. This provides a new perspective on why some stars burn fuel at vastly different rates despite having similar core temperatures. By Orion Carl Daly 6. Cookbook for the Universe. C. The sequence of stellar nucleosynthesis. The order in which elements form is not random or solely heat-dependent, but follows a progressive set of impedance shifts, each allowing a new class of elements to emerge. For example, carbon fusion begins only when the relative equilibrium between helium nuclei stabilizes within a star's energy framework, not just when temperature thresholds are met. 2.4 Fusion as an alternating current AC energy exchange. Another way to understand fusion in the relative gravity model is as an alternating current AC interaction rather than a simple unidirectional nuclear reaction. In classical physics, energy from fusion is thought to radiate outward in a mostly linear fashion as heat and light. In relative gravity, energy oscillates cyclically through spatial-time impedance adjustments, resembling an AC waveform where the star's relative mass fields oscillate, creating synchronized energy pulses. Fusion zones act as resonant amplifiers, enhancing or inhibiting reactions based on local impedance and wave coherence. 2.5 The role of spatial time in fusion efficiency. A major innovation of the relative gravity approach is recognizing that fusion efficiency is not absolute but dependent on a star's spatial-time relationship with its surrounding environment. Classical view: fusion is a function of temperature, pressure, and available nuclear material. Relative gravity view: fusion is a function of spatial-time flow, which determines the rate of energy transfer and resonance stability within the stellar manifold. This offers an explanation for why stars of similar size and composition may burn at vastly different rates. Each exists within a unique spatial-time condition, which governs the impedance balance necessary for efficient fusion. By Orion Carl Daly 7. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. 2.6 In recap. Fusion is not just the result of high temperature and pressure, but is governed by a star's impedance balance and energy superposition. Relative equilibrium points define where and how efficiently fusion occurs, shaping the structure and evolution of stars. Fusion rates and nucleosynthesis sequences are tied to spatial-time flow, affecting element formation and stellar longevity. The AC-like behavior of stellar energy cycles suggests that nuclear reactions are self-regulating within resonant structures, rather than purely heat-driven. By shifting the focus from gravitational compression models to relative force and impedance balancing, relative gravity offers a deeper, more interconnected explanation for stellar fusion, one that ties together the dynamics of energy exchange, nucleosynthesis, and cosmic evolution. By Orion Carl Daly 8. Cookbook for the Universe 3. The role of impedance in element formation. The role of impedance in element formation. In the relative gravity (RG) framework, impedance is a fundamental concept governing how energy moves, transforms, and interacts within stellar interiors. While conventional astrophysics explains fusion in terms of temperature, pressure, and nuclear binding energy, relative gravity extends this understanding by treating impedance as a key determinant of energy exchange efficiency within a star's manifold. 3.1 What is stellar impedance? Impedance in relative gravity is analogous to electrical resistance in a circuit. It defines how efficiently energy can move through a medium. In an electrical system, impedance determines how much current flows in response to a given voltage. In a star, impedance dictates how efficiently nuclear reactions occur, how energy propagates, and where fusion can or cannot proceed. Key insight: a star is not just a hot plasma sphere, it is an energy processing system where impedance regulates element formation, energy distribution, and ultimately, stellar evolution. 3.2 Factors affecting impedance in stars. The impedance of a star is not constant, it varies based on A. Density and composition of the stellar plasma. The more dense the plasma, the more energy it can retain. Different elements have different atomic impedance values, affecting their fusion likelihood. B. The surrounding gravitational field. Stronger gravity increases confinement pressure, affecting how energy interacts with the stellar medium. A higher gravitational field strength alters the energy flow, potentially lowering or raising impedance. By Orion Carl Daly 9. Aka, Essay on Relative Gravity to describe the mechanics of the universe. C. Temperature and radiation pressure. Higher temperatures reduce impedance by allowing particles to collide with greater force. Radiation pressure creates feedback loops that can either sustain fusion or increase impedance saturation, halting reactions. Relative gravity perspective. Impedance is not a simple function of density or pressure. It is a dynamic, self-regulating property of a star's energy equilibrium. 3.3 Impedance and the fusion limit. Why does fusion stop at iron? In classical astrophysics, fusion halts at iron Phi because fusion beyond iron is endothermic, it consumes more energy than it produces. Iron nuclei are the most tightly bound, making further fusion inefficient. In relative gravity, this process is understood through impedance saturation. As a star undergoes fusion, energy transfer reaches a point of maximum impedance where energy movement becomes inefficient. The core structure reaches a state where energy can no longer be effectively channeled outward, leading to a collapse or transition event: supernova, neutron star formation, or black hole formation. 3.3.1 Key difference. Instead of just seeing iron as an endpoint due to energy constraints, RG views it as an impedance threshold where energy exchange becomes unsustainable within the star's structure. By Orion Carl Daly 10. Cookbook for the Universe. 3.4 Why do massive stars evolve differently from low-mass stars? In conventional models, a star's mass determines its evolution. A. Low-mass stars' 8 solar masses end as white dwarfs after helium fusion. B. Massive stars' 8 solar masses undergo extended fusion cycles before supernova. However, in relative gravity, a star's evolutionary pathway is dictated not only by its mass but by the impedance profile of its core. C. Lower mass stars have higher relative impedance due to weaker gravity and lower pressure. Impedance prevents extended fusion cycles, leading to early cessation of nucleosynthesis and white dwarf formation. D. Higher mass stars possess lower core impedance, enabling sustained fusion beyond helium. Can undergo carbon, oxygen, neon, and silicon fusion, forming heavier elements before reaching iron saturation. Key insight: instead of just mass, the internal impedance structure of a star dictates how long fusion continues and which elements form. 3.5 Supernova as alternating current AC events. A supernova explosion is one of the most extreme energy events in the universe. Conventional physics treats it as a thermal and nuclear runaway process, but in relative gravity, a supernova is seen as a cosmic capacitor discharge event, where energy is released due to an impedance collapse. See analogy. In an electrical circuit, a capacitor stores energy until its dielectric limit is exceeded, at which point the energy is released in a high-voltage pulse. In a supernova, the stellar core accumulates energy until impedance saturation is reached. at which point a sudden phase transition discharges energy outward. By Orion Carl Daly 11. Aka, Essay on Relative Gravity to describe the mechanics of the universe. 3.6 How impedance collapse triggers a supernova. A. Iron core formation, right arrow energy absorption exceeds release, leading to impedance saturation. B. No further fusion, right arrow energy is no longer effectively transferred outward. C. Collapse to equilibrium, right arrow the star contracts rapidly, forcing matter into higher impedance states. D. Shockwave discharge, right arrow stored energy releases explosively, dispersing elements and triggering nucleosynthesis in surrounding space. Key insight: a supernova is not just a catastrophic collapse but an impedance-driven release event, where stored energy is suddenly converted into an outward propagating force. 3.7 Impedance and element formation in supernova. During a supernova, new elements form through rapid neutron capture or process. However, instead of this being purely heat-driven, relative gravity explains it as a reconfiguration of impedance networks within high-energy plasma states. The impedance of the ejecta dictates which elements form in what regions. Neutron-rich environments experience localized impedance shifts, enabling the formation of gold, platinum, and uranium. By Orion Carl Daly 12. Cookbook for the Universe. Key difference: instead of treating supernova nucleosynthesis as chaotic, relative gravity suggests it follows structured impedance pathways, determining which elements form where and in what quantities. 3.7 Summary: the role of impedance in element formation. A. Impedance regulates fusion efficiency. It is the key factor that determines where and when fusion reactions occur. B. Fusion halts at iron due to impedance saturation, not just energy constraints. Beyond this point, energy cannot flow effectively, leading to core collapse. C. Massive stars continue fusion longer because of lower core impedance, allowing for more extended nucleosynthesis cycles. D. Supernova function as alternating current AC events, where energy release is governed by an impedance collapse model. E. Heavy element formation in supernova follows structured impedance pathways, meaning the distribution of elements in space is not random, but follows systematic energy transformations. By integrating impedance as a governing principle of stellar evolution, relative gravity provides a unified framework explaining not just why fusion happens, but why it follows distinct patterns, unlocking a deeper understanding of element formation, supernova, and cosmic energy exchange. Supernova as alternating current events. In classical physics, a supernova is described as a catastrophic gravitational collapse, where a massive star exhausts its nuclear fuel, leading to an implosion followed by an explosive rebound. While this model captures the basic mechanisms, it does not fully explain the structured nature of energy release, the selective formation of elements, and the resonance effects observed in supernova. In relative gravity RG, supernova are not just explosions, they are phase transitions in stellar alternating current AC cycles. Celestial bodies, rather than interacting through static gravitational forces alone, are governed by oscillatory energy relationships, where energy propagates in wave-like resonant states. A supernova represents an extreme phase shift in these oscillatory interactions, leading to a sudden reconfiguration of energy pathways and element formation. By Orion Carl Daly 13. Aka, Essay on Relative Gravity to describe the mechanics of the universe. 4.1 The supernova as an AC discharge event. A key tenet of relative gravity is that celestial bodies behave like dynamic energy systems, where energy is continuously stored, transformed, and released in structured cycles. In this framework, a supernova is analogous to a capacitor discharge event in an electrical circuit, where a sudden collapse of impedance triggers an explosive release of stored energy. In an electrical capacitor, energy accumulates until the dielectric material reaches its breakdown voltage. Once exceeded, the capacitor rapidly discharges, releasing energy in a sudden burst. 4.1.1 In a supernova, energy is stored as nuclear binding energy within the stellar core. As the iron core forms, impedance reaches a maximum, creating an energy bottleneck. When outward radiation pressure fails, the core collapses and energy is explosively discharged into space, forming new elements. Key insight: a supernova is not merely an uncontrolled explosion, it is a highly structured energy redistribution event, governed by impedance shifts and AC wave interactions. by Orion Carl Daly 14. Cookbook for the Universe 4.2 The supernova collapse process as an impedance breakdown. The stages of a supernova align closely with the breakdown of an accregulated energy system. 4.2.1 Impedance reaches maximum fusion stops. As a massive star reaches the iron fusion limit, no further energy can be extracted from nuclear fusion. Impedance within the core increases, creating a bottleneck where energy can no longer be effectively transferred outward. This is the stellar equivalent of a capacitor reaching its maximum charge before discharge. 4.2.2 Loss of radiation pressure triggers collapse. When outward radiation pressure drops, gravity overcomes thermal support, and the core collapses in milliseconds. The core enters a high-energy resonance state, where energy is compressed into a superposition of quantum states. This phase is analogous to an overcharged capacitor where the dielectric material gives way, allowing energy to be released. 4.2.3 The explosion as a stellar discharge event. The star's collapse generates a sudden shift in relative mass equilibrium, leading to ZR resonance emission. Electromagnetic shock waves and neutrino fluxes interact with outer stellar layers, triggering the supernova explosion. Energy is redistributed outward in wave-like patterns, much like a high-frequency AC pulse. Key difference: conventional models describe a supernova as a single event. The relative gravity views it as an energy phase transition within a larger cosmic cycle. By Orion Carl Daly 15. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. 4.3 Supernova shock waves as resonance waves. A supernova releases energy in structured wave fronts, resembling alternating current frequency modulation. This explains why supernova remnants form distinct filamentary structures. Energy is not expelled chaotically, but follows pre-existing impedance pathways within the surrounding plasma. Why pulsars and magnetars emerge from some supernova. The collapse process leaves behind a resonant electromagnetic structure. Why gamma-ray bursts are associated with supernova. High-energy resonance fields oscillate in extreme bursts, similar to a capacitor discharging at high frequency. Implication: supernova are not just random explosions but harmonic events that follow alternating current principles, regulating how energy is distributed in space. 4.4 The role of ZR resonance emission in supernova. One of the most critical concepts in relative gravity is ZR resonance emission, which occurs when a system experiences a sudden shift in relative mass equilibrium. In the context of a supernova, as the core collapses, mass-energy relationships undergo a rapid transition. This generates resonant emissions, where energy propagates outward in structured wavefronts. These emissions seed the interstellar medium with newly synthesized elements, forming the building blocks for new stars and planetary systems. How ZR resonance guides element formation. Lighter elements C, O, C, V form in layered fusion shells before the explosion. Heavier elements gold, platinum, uranium form through rapid neutron capture are processed during core collapse, where relative mass fluctuations create the necessary conditions for extreme nucleosynthesis. The ZR resonance wavefront propagates outward, dispersing elements across galaxies in a structured distribution. Key takeaway: the chemical makeup of the universe is not random but follows patterns dictated by impedance resonance and mass energy shifts. By Orion Carl Daly 16. Cookbook for the Universe 4.5 The connection between supernova and cosmic energy circuits. If supernova are alternating current events, then they serve as energy regulators in a larger cosmic circuit. Just as electrical grids use transformers to regulate current flow, supernova act as stellar transformers, redistributing matter and energy across galaxies. This suggests that the universe operates as a self-balancing energy network, where supernova reset local impedance conditions, influencing the evolution of surrounding systems. Implications for cosmology. A. The large-scale structure of the universe. Cosmic filaments and voids may be structured based on supernova-driven impedance shifts, not just gravity alone. B. The origin of galactic magnetic fields. Supernova may serve as natural AC generators, contributing to large-scale magnetic field formation. C. Black holes as energy recyclers. Some supernova remnants collapse into black holes, which may function as induction loops, feeding energy back into the cosmic circuit. Big picture insight. The universe is not an isolated system of gravitational interactions but a self-regulating, galaxy-driven energy network where supernovae play a fundamental role in redistributing mass, generating resonance states, and structuring cosmic evolution. 4.6 Summary: Supernova as icy events. Supernova act as phase transitions in stellar alternating current AC cycles, where equilibrium is violently disrupted. The explosion is triggered by impedance collapse, similar to a capacitor discharge. Supernova shock waves follow resonance wave fronts, explaining structured remnant formations and gamma-ray bursts. ZR resonance emission guides the formation of heavy elements, ensuring a structured distribution of matter in space. Supernova are part of a larger cosmic circuit, functioning as energy transformers that regulate mass-energy relationships on a galactic scale. By Orion Carl Daly, 17. Aka, Essay on Relative Gravity to describe the mechanics of the universe. By treating supernova as structured energy redistribution events rather than chaotic explosions, relative gravity provides a unifying framework linking stellar evolution, element formation, and cosmic structure into a single dynamic system. 5. Neutron star mergers, black holes, and the delta phenomenon. Neutron stars and black holes represent the densest and most extreme states of matter in the universe, where gravity, energy, and space-time interact in ways that defy classical intuition. In conventional astrophysics, neutron star mergers and black hole formation are treated primarily as gravitational events, with their influence on element formation and cosmic evolution being secondary considerations. However, in relative gravity (RG), these events are fundamental energy phase transitions, where matter undergoes reconfiguration at maximum impedance states, leading to structured nucleosynthesis, gravitational wave emission, and space-time resonance phenomena. A key principle within relative gravity is the delta phenomenon, which describes how manifolds evolve through cycles of energy transformation and matter organization. In this framework, neutron star mergers act as resonant amplification events, producing the heaviest elements in the universe. Black holes function as spatial induction engines, cycling mass-energy interactions across cosmic scales. The delta phenomenon ensures that energy and matter are not static but undergo iterative phase transitions, contributing to cosmic evolution. 5.1 Neutron star mergers, the universe's heavy element factory. Neutron star mergers are now recognized as the primary site for rapid neutron capture nucleosynthesis (R) process, responsible for producing gold, platinum, uranium, and other heavy elements. In classical astrophysics, these mergers are seen as violent, high-energy collisions where extreme pressures and temperatures enable exotic nuclear reactions. However, in relative gravity, neutron star mergers are more than high-energy collisions. They are resonance events in spatial time, where two massive objects oscillate toward a synchronization threshold before undergoing a phase collapse into a unified structure. This process resembles alternating current transformers, where energy is reconfigured, amplified, and redistributed in high-frequency waveforms. By Orion Carl Daly, 18. Cookbook for the Universe 5.1.1 How Impedance and Resonance Shape Neutron Star Mergers. A. Pre-merger oscillation. Relative force interactions. As two neutron stars spiral toward each other, their gravitational fields create an oscillatory feedback loop, resembling a dual-phase AC circuit. This feedback intensifies neutron density, priming the system for extreme nucleosynthesis. Gravitational waves act as energy release valves, allowing the merger to approach a synchronized resonance state. B. The moment of merger. Phase collapse impedance transition. The two stars merge when their relative equilibrium reaches a breaking point, triggering an impedance collapse where nuclear binding energies become unstable. This breakdown leads to a surge in neutron density, enabling our process element formation. Gamma-ray bursts, where excess energy is discharged in high-frequency wavefronts. The formation of a hypermassive neutron star or black hole, depending on mass constraints. C. Post-merger energy redistribution, ZR resonance emission. A newly formed object undergoes ZR resonance emissions, where mass-energy interactions stabilize. The remaining neutron-rich ejecta expands outward, carrying newly synthesized gold, platinum, and actinides into interstellar space. This ensures that future generations of stars and planetary systems inherit these elements, forming the chemical foundation of rocky planets and biological systems. Key insight: Instead of viewing neutron-star mergers as chaotic collisions, relative gravity models them as structured resonance amplifiers, where alternating current energy states regulate the formation of the universe's rarest elements. By Ryan Carl Daly 19. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. 5.2 Black Holes, Spatial Induction Engines. Black holes have traditionally been seen as gravitational singularities where matter collapses into an infinitely dense point, beyond which nothing can escape. However, this view treats black holes as end states rather than dynamic components of cosmic evolution. In relative gravity, black holes function as spatial induction engines, where mass energy undergoes transformation rather than destruction. Instead of a one-way gravitational trap, black holes regulate the movement of energy across space-time. 5.2.1 How black holes process energy matter. A. Event horizon as an impedance boundary. The event horizon is not a point of no return, it is a threshold where impedance prevents normal energy transmission. Matter crossing the event horizon is not destroyed but undergoes an impedance shift, altering its interaction with space-time. By Ryan Carl Daly 20. Cookbook for the Universe. B. The core is a resonance chamber. Inside a black hole, relative mass fields oscillate at extreme frequencies, generating spatial-time distortions. This creates a standing wave phenomenon where energy cycles between absorption and emission states. Hawking radiation and relativistic jets can be seen as leakage points where energy escapes through phase shifts rather than direct gravitational repulsion. C. Matter recycling cosmic reorganization. Instead of simply devouring matter, black holes act as mass energy recyclers, breaking down complex structures into low-impedance waveforms. Some of this energy reemerges in different space-time frames, potentially linking black holes to white hole formation or multiversal transitions. Key insight: black holes do not represent an absolute loss of information. Instead, they are high-impedance, energy-sorting mechanisms, essential for maintaining cosmic balance. 6. The delta phenomenon. Cosmic evolution as iterative phase shifts. The delta phenomenon in relative gravity describes how manifolds evolve through cycles of transformation. Instead of viewing the universe as a linear progression from one state to another, the delta phenomenon suggests that cosmic structures undergo iterative shifts, continuously refining their properties through energy exchange. 6.1 How the delta phenomenon shapes cosmic evolution. A. Stars evolve through impedance shifts. As a star ages, it undergoes nucleosynthesis cycles dictated by relative force and impedance balancing. When a threshold is reached, supernova, merger, black hole formation, a delta shift occurs, transforming the system into a new state. B. Neutron-star mergers represent delta evolution in nucleosynthesis. Heavy elements are not formed progressively in stars but through discrete phase transitions. The merging of two neutron stars is a delta shift, where high-density matter reorganizes into a new elemental composition. By Ryan Carl Daly 21. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. C. Black holes represent delta energy reprocessing. Matter-energy interactions do not cease at black holes, they enter a new phase of cosmic evolution. Black holes may serve as energy-sorting mechanisms, directing matter into new cosmological structures. Key insight: the universe does not evolve linearly but cyclically, with neutron-star mergers, black holes, and stellar collapse acting as delta thresholds, where cosmic matter energy transitions into new configurations. 6.2 Summary: the cosmic role of neutron stars, black holes, and the delta phenomenon. Neutron-star mergers function as resonance amplifiers, where heavy elements form through structured impedance shifts. Black holes serve as spatial induction engines, regulating the movement of energy across the universe. The delta phenomenon explains how cosmic structures evolve iteratively, shifting energy and matter through discrete transformation events. The universe is a dynamic, alternating current system, where stellar interactions continuously rebalance energy across time and space. By integrating relative gravity as impedance and resonance framework, we see that neutron stars and black holes are not isolated phenomena. They are part of a larger cosmic cycle of energy redistribution and matter transformation, ensuring the universe remains an evolving, structured system. By Ryan Carl Daly 22. Cookbook for the Universe 7. The universe as a stellar nucleosynthesis network. Taking a step back, Relative gravity (RG) redefines stellar nucleosynthesis not as an isolated process, but as part of an interconnected cosmic network, where energy, matter, and forces evolve through iterative cycles of transformation. Instead of treating stars as independent element factories, RG views them as nodes in a vast system of energy superposition, impedance regulation, and mass exchange across time and space. In this model, stellar nucleosynthesis is governed by three fundamental principles. 7.1 Key governing principles of the nucleosynthesis network. 7.1.1 The delta phenomenon. Element formation follows an iterative cycle of transformation, where mass-energy relationships continuously evolve rather than remaining static. Each phase of stellar evolution represents a new iteration in nucleosynthesis, allowing elements to emerge based on the resonance conditions of the surrounding space-time manifold. This framework explains why element formation is not arbitrary, but follows a structured evolutionary pattern. By Ryan Carl Daly, 23. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. 7.1.2 Polymorphism of Forces. Nucleosynthesis and gravitational dynamics do not function independently. They operate under a shared framework of energy conservation and exchange. Fusion, supernova, and black hole formation are not separate astrophysical events but interrelated phenomena, driven by relative equilibrium adjustments within the cosmic medium. Forces behave polymorphically, meaning that the same fundamental principles govern both micro-scale nuclear interactions and large-scale gravitational phenomena. 7.1.3 Manifold interactions. Each star is not an isolated entity, but a self-contained system interacting with the larger stellar evolution network. Relative mass exchanges between stars, interstellar clouds, and compact objects affect the flow of nucleosynthesis over cosmic timescales. Supernova remnants, neutron star mergers, and black hole accretion disks distribute elements in structured ways, influencing the formation of future stars and planetary systems. 7.2 Why is this important? 7.2.1 Unifying nuclear fusion, stellar dynamics, and cosmic evolution. Rather than treating nuclear fusion, gravitational interactions, and cosmic element distribution as separate domains, RG provides a single, object-oriented model that integrates them into a cohesive framework. Element formation follows structured resonance patterns, rather than occurring randomly at specific temperatures. Supernova, neutron star mergers, and black holes serve as phase transition points, regulating energy redistribution across the cosmic web. Fusion efficiency is dictated by impedance harmonics, meaning that each stellar life cycle follows a predictable path based on local energy constraints. 7.2.2 Connecting nucleosynthesis with quantum mechanics. Why do elements form in specific sequences? The answer lies in the harmonic resonance between energy fields, impedance conditions, and spatial time differentials. By Ryan Carl Daly, 24. Cookbook for the Universe. Why does fusion efficiency vary across different stellar types? Each star operates within a unique impedance-regulated energy framework, influencing how energy is absorbed, stored, and released. How does quantum behavior scale to cosmic dynamics? The principles of superposition, resonance, and relative equilibrium apply at both the atomic and interstellar scales, bridging quantum mechanics with astrophysical evolution. 7.2.3 Reinterpreting stellar life cycles through energy superposition. Stars do not randomly ignite, burn, and explode. They follow structured paths determined by their relative equilibrium states within the energy superposition framework. Each stage of a star's life is not simply a thermonuclear reaction, but an adjustment within the impedance matrix of the cosmic medium. The stopping point at iron is not just about energy constraints but reflects the saturation of impedance balance, preventing further nucleosynthesis in conventional fusion sequences. 7.3 Conclusion. Rethinking stellar evolution with relative gravity. The relative gravity perspective offers a fundamental shift in understanding how stars, matter, and cosmic forces interact. 7.3.1 Fusion is a function of relative equilibrium, not just nuclear force. Energy flow within a star is governed by impedance-regulated pathways, rather than simple thermal pressure and gravitational compression. 7.3.2 Supernova and neutron star mergers are phase transitions in energy superposition. These events do not represent random explosions but structured rebalancing processes, redistributing energy across multiple scales. 7.3.3 Impedance saturation explains why element formation stops. 7.3.4 Black holes might not just be endpoints but part of a larger recycling mechanism. Black holes function as spatial induction engines, reorganizing mass-energy interactions rather than permanently removing matter from the universe. By Orion Carl Daly, 25. Aka, Essay on Relative Gravity to describe the mechanics of the universe. 7.3.5 The universe operates as a nucleosynthesis network, driven by cycles of relative force exchange. Stars, supernova, neutron stars, and black holes act as nodes in a dynamic energy circuit, ensuring that matter continues to evolve across cosmic timescales. 7.4 The Big Picture: Cosmic Resonance and the Evolution of Matter. Stellar nucleosynthesis is not just the byproduct of gravity and nuclear forces, it is an expression of cosmic resonance, impedance harmonics, and iterative mass-energy evolution. The universe functions as a massive, interconnected system where nucleosynthesis is regulated through alternating current-like energy interactions. Each star, galaxy, and cosmic structure exists within a self-regulating framework of energy transformation, guided by relative mass interactions, resonance feedback, and impedance constraints. Matter is never lost, only reorganized through delta phenomenon phase transitions, ensuring the continual synthesis and redistribution of elements throughout the cosmos. By viewing the universe not as a collection of separate astrophysical phenomena, but as an interconnected nucleosynthesis network, relative gravity provides a framework for understanding how matter evolves, why elements form in structured patterns, and how cosmic forces interact to maintain equilibrium. 7.5 Next step: the formation of our solar system. With this cosmic scale understanding of element formation and energy distribution, we now turn to how these processes govern the creation of our own solar system. How the Sun's nucleosynthesis shaped planetary composition. Why each planet has a unique elemental structure based on impedance and resonance interactions. How gravitational tides, solar wind, and energy equilibrium shape the distribution of heavy elements in the early solar system. By Orion Carl Daly, 26. Cookbook for the Universe 8 The Sun imparting elements to the planets. Why each planet is unique. In the framework of relative gravity (RG), the distribution of elements in the solar system is not just a result of gravitational collapse and accretion, but is fundamentally shaped by relative equilibrium, impedance, and resonance interactions between the Sun and each planet. Instead of a static gravitational model, the solar system is an interconnected energy network, where each planet's unique characteristics emerge from spatial-time interactions, mass resonance, and solar energy exchange. 8.1 The Sun's role in element distribution. The Sun, as the central energy source of the solar system, continuously imparts energy, plasma, and elements through a dynamic interplay of solar wind, stellar nucleosynthesis, and energy resonance effects. These mechanisms dictate which elements accumulate where and shape planetary evolution. A. Solar wind and element transport. The solar wind, a stream of charged particles, electrons, protons, and trace heavy elements, extends outward, influencing planetary atmospheres, magnetic fields, and surface compositions. Planets with strong magnetic fields, e.g., Earth, Jupiter, Saturn, dynamically interact with the solar wind, capturing or deflecting particles based on impedance. By Orion Carl Daly, 27. Aka, Essay on Relative Gravity to describe the mechanics of the universe. Resonance shielding. Planets with weak or no magnetic fields, e.g., Mars, Venus, experience gradual atmospheric stripping, where lighter elements are lost to space due to energy exchange with solar plasma flows. Relative gravity insight. Solar wind interactions are not uniform across the solar system. They depend on planetary mass, relative impedance, and orbital resonance states. B. Stellar nucleosynthesis residue in the protosolar cloud. The chemical composition of the solar system is a product of past stellar nucleosynthesis, shaped by supernova remnants, neutron star mergers, and cosmic dust accumulation before the Sun formed. The Sun's molecular birth cloud was enriched with elements from prior generations of stars, distributing lighter elements hydrogen, helium across the entire solar system. Metals and heavier elements carbon, oxygen, silicon, iron, uranium within localized regions of high impedance. Impedance sorting played a key role in how these elements were distributed within the protoplanetary disk, influencing planetary core formation and chemical differentiation. Relative gravity insight. Element sorting is not random. It follows the resonance emissions and relative force superposition, defining where metals, silicates, and volatiles accumulate. By Orion Carl Daly 28. Cookbook for the Universe C. The T-Tauri phase element sorting. During its early evolution, the Sun underwent a T-Tauri phase, marked by intense stellar winds that fundamentally shaped planetary compositions. How this affected the inner planets. Lighter elements hydrogen, helium were expelled from the inner solar system, leading to the formation of rocky planets Mercury, Venus, Earth, Mars. High-energy radiation increased surface impedance, limiting the retention of volatile compounds. How this affected the outer planets. Gas giants Jupiter, Saturn formed beyond the solar snow line, where low impedance zones allowed gas accumulation. This explains why Jupiter and Saturn retained hydrogen-helium atmospheres, while the inner planets did not. Relative gravity insight. The T-Tauri phase was a resonance realignment event, where mass sorting and impedance thresholds defined planetary compositions. By Orion Carl Daly 29. Aka, Essay on Relative Gravity to describe the mechanics of the universe. 8.2. Why each planet is unique. Each planet functions as its own manifold, with unique properties determined by relative mass, resonance with the Sun, and spatial-time interactions. A. Orbital resonance spatial-time. Each planet occupies a distinct orbital resonance, meaning its interaction with the Sun follows harmonic energy absorption patterns. Relative equilibrium between planetary mass and solar energy influx dictates which elements are retained. Example: Mercury, being closest to the Sun, experiences extreme radiation, which strips away volatile compounds, leading to its high-density iron core. Outer planets Jupiter. Saturn retain massive gaseous envelopes because their relative mass and distance create a different impedance balance with the Sun. Relative gravity insight. Planets lock in their unique compositions through orbital resonance conditions, ensuring elemental differentiation follows structured energy pathways. B. Mass, gravity, and atmospheric composition. A planet's ability to retain an atmosphere depends on its relative mass and gravitational impedance balance with the solar wind. Lighter planets, e.g. Mars, have weaker gravitational fields, losing volatile elements over time. By Orion Carl Daly 30. Cookbook for the Universe. Massive planets, e.g. Jupiter, Saturn, have lower impedance thresholds, allowing them to retain thick atmospheres. Relative gravity insight. Atmospheric retention is not just a function of gravity, it depends on impedance balance, magnetic shielding, and orbital resonance interactions. C. Elemental distribution. Rocky versus gas giants. The inner planets Mercury, Venus, Earth, Mars are rocky because the T-Tauri winds expelled lighter elements. High impedance near the Sun prevented gas accumulation. The outer planets Jupiter, Saturn, Uranus, Neptune are gas giants because their regions had lower impedance, allowing the accumulation of hydrogen, helium, and methane. D. Magnetic fields elemental protection. Planets with strong magnetic fields Earth, Jupiter, Saturn retain their atmospheres by deflecting charged solar particles. Planets with weak or no magnetic fields Mars, Venus experience atmospheric loss over time. Relative gravity insight. Magnetic fields act as impedance shields, regulating solar particle interactions and atmospheric retention. E. Water and chemical evolution. Earth retained water due to its relative mass equilibrium, magnetic shielding, and habitable zone positioning. Venus lost its water due to runaway greenhouse effects, where trapped solar energy evaporated and dissociated water molecules. Mars had water but lost it due to weak gravity and the gradual loss of its magnetic field. Relative gravity perspective. Water retention depends on spatial time, impedance, and energy regulation, not just temperature alone. By Ryan Carl Daly 31. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. 8.3. Summary. Why each planet is its own planet. Each planet's uniqueness results from its interaction with the Sun's energy and matter through relative equilibrium and spatial time impedance. Factor effect on planet formation properties. Relative mass determines gravitational pull and ability to retain elements. Regulates energy exchange, defining atmospheric impedance balance composition. Orbital resonance affects solar energy absorption and climate dynamics. Shields the planet from solar wind, influencing atmospheric magnetic fields evolution. Elemental distribution defines whether a planet is rocky, gaseous, or icy. 8.3.1 Key takeaway. Each planet is a dynamically balanced system, existing at a unique relative equilibrium with the Sun. Their properties are not random, but shaped by energy interactions, plasma flows, and resonance fields within the solar system. 8.3.2 Final thoughts. This refined section integrates relative gravity principles into the standard planetary formation model, showing that planets form and evolve based on energy dynamics, not just gravitational accretion. By Ryan Carl Daly 32.